The webpage details the Seizure Detection Challenge 2025, an international competition that invites researchers and developers to create machine learning models capable of detecting epileptic seizures from long-term EEG recordings. Below is an overview of the key aspects of the challenge. Overview. Objective. Participants must build models that analyze continuous EEG recordings to detect the onset and duration of epileptic seizures. The task is framed as a segmentation problem where the model outputs a head-score compliant tab-separated values TSV file listing each seizure event. Impact. With epilepsy affecting over 50 million people worldwide, improvements in EEG-based seizure detection can enhance diagnostic workflows and ultimately patient care. However, progress has been hampered by limited public datasets and non-standardized evaluation methodologies. This challenge leverages the ESCOR standard to address these issues. Cite, turn, zern, fetch. Challenge details. Input signal, long-term EEG recordings stored in .def files containing 19 channels based on the international 10 to 20 system. Signals are recorded at 256 Hz and each recording lasts at least 10 minutes, with most lasting around 1 hour. Model output. The model must output a TSV file with 1 row per detected seizure event. Each row includes the onset time in seconds, duration in seconds, seizure type, always starting with SZ for seizure events, and additional fields, e.g. confidence and channels, which are not evaluated. Training data. Participants can train their models on any combination of publicly available EEG datasets or private datasets. The main public datasets include the CHB-MIT SCALP EEG database, TUH EEG-Z corpus, and Sienna SCALP EEG database. A specialized Python library, ESL epilepsy 2-BIDS, is provided to convert these datasets into the standardized format required by the challenge. Evaluation. Submissions are scored based on an event-based F1 metric computed over a large holdout dataset, more than 2,500 hours of EEG data. The evaluation considers factors such as any overlap between the detected event and the reference event, with additional pre-ictal and post-ictal tolerances, and merges or splits events based on duration thresholds. Participants must submit their pre-trained model as a Docker image that processes input from a read-only/data volume and writes results to a writable/output volume. The Docker image should use environment variables input and output to specify file paths, and a command is provided as an example to execute the model. Cite turn fetch 0 submission form. The form requires details such as the algorithm's title, registry path for the Docker image, author list, abstract, license, datasets used, and optional repository or publication details. Limitations. Each participant is allowed a maximum of 3 submissions. In addition to the algorithm, teams may submit a poster with additional details about their approach. The holdout dataset in this challenge refers to a large private dataset, over 2,500 hours of EEG recordings, that is used exclusively for evaluating participants' models. This dataset is not made available for training or tuning models. Instead, it is kept secret to ensure that models generalize well to unseen data and are not overfitted to known public datasets. Why use a holdout dataset? 1. Fair evaluation. Since all participants train on the same public datasets, using a private holdout set ensures models are fairly compared on unseen data. 2. Generalization. Prevents overfitting by testing models on new EEG recordings. 3. Clinical relevance. Ensures real-world applicability by evaluating models on diverse, independent data. How is it used? Once a participant submits their model, it is evaluated on the holdout dataset. The scoring is based on the event-based F1 score, which measures seizure detection accuracy. In the event of a tie, sensitivity, the ability to detect actual seizure events, is used as a secondary evaluation metric. This approach ensures that the best models truly excel in real-world seizure detection, rather than simply memorizing patterns from training data. The event-based F1 score is the primary evaluation metric used in the Seizure Detection Challenge 2025 to assess how well models detect entire seizure events from EEG recordings. Unlike point-based scoring, which evaluates each individual EEG sample, event-based scoring considers whether a predicted seizure overlaps with an actual seizure. This ensures that models are rewarded for detecting full seizures rather than just short segments. The F1 score is a harmonic mean of precision and recall, where precision measures how many predicted seizures are actual seizures, and recall measures how many real seizures the model detects. The formula for F1 score is F1 equals 2 times fraxed precision times text precision plus text recall. Precision positive predictive value is calculated as true positives, TP, true positives, false positives, FP, while recall sensitivity is calculated as true positives, false negatives, FN. In the challenge, an event is considered a true positive if the predicted seizure overlaps with a real seizure. If a model predicts a seizure that does not match any real event, it counts as a false positive, and if a real seizure is missed entirely, it counts as a false negative. To account for slight variations in seizure timing, the evaluation introduces temporal tolerances. A model's prediction can be counted as correct if it occurs up to 30 seconds before the actual seizure, pre-ictal tolerance, or up to 60 seconds after the seizure ends, post-ictal tolerance. Additionally, seizures that separated by less than 90 seconds are merged, while seizures longer than 5 minutes are split into multiple events. For example, consider a real dataset where 3 seizures occur at 296, 40's duration, 453's, 12s duration, and 895's, 21's duration. If a model predicts seizures at 295's, 38's duration, 460's, 10's duration, 900's, 19's duration, and 1200's, 15's duration, then 2 of the predictions correctly overlap with real seizures, TP, while 2 are false positives, FP, and 1 real seizure is missed, FN. Using the formulas for precision and recall, the F1 score would be computed accordingly. This event-based scoring method is preferred because it provides a clinically meaningful evaluation, ensuring that models not only detect seizures accurately, but also avoid excessive false detections. A higher F1 score indicates a model that achieves the right balance between precision and recall, making it more reliable for real-world seizure detection applications. ESCOR is a technically rich, rigorously detailed, and refreshingly collaborative framework designed to standardize how EEG-based seizure detection algorithms are validated. At its core, the framework demands that EEG recordings conform to strict standards. Data must be stored in .edf files following the EEG-BIDS guidelines, with a fixed 1020 montage, 19 electrodes in a specific order, and a sampling rate of 256 Hz. This uniformity is crucial because it enables researchers to compare algorithms across diverse datasets without being tripped up by discrepancies in channel configurations, montages, or file formats. Tools like the Epilepsy 2 BIDS library help convert various public datasets into this standardized format, which is a neat solution to a long-standing headache in the field. On the evaluation side, ESCOR isn't shy about diving into the technical nitty-gritty. It prescribes both sample-based and event-based scoring methods. Sample-based scoring, with labels provided at a 1 Hz resolution, caters to the machine learning aficionados who love granular, second-by-second analysis. In contrast, the event-based scoring method is where clinical relevance really shines. After all, the key question is, how many seizures did the patient have? To tackle this, the framework employs some quirky yet pragmatic parameters: a 30-second pre-ictal tolerance to allow for early detection, a 60-second post-ictal tolerance to account for delayed responses, merging of events separated by less than 90 seconds, and splitting events longer than 5 minutes. While these numbers might initially seem arbitrary, they are thoughtful responses to the inherent variability in human annotation and the messy reality of EEG signals. Moreover, ESCOR lays out robust cross-validation strategies. For personalized models, time series cross-validation ensures that training data always precede the test data, a must for applications where a model needs to adapt to a single patient's evolving EEG patterns. For subject-independent models, techniques like leave one out or k-fold cross-validation are recommended to maintain strict independence between training and test sets, thereby preventing overfitting and offering a realistic estimate of model performance. SysCore's insistence on high-quality, clinical-grade EEG recordings with a full 10 to 20 montage might limit its immediate applicability to emerging wearable or subcutaneous EEG systems, which often come with their own set of challenges, like lower signal quality or non-standard electrode placements. However, the authors acknowledge these limitations and hint at future adaptations to embrace these new technologies. In summary, ESCOR is not only a technical tour de force, meticulously detailing everything from data formats and cross-validation strategies to performance metrics like sensitivity, precision, and F1 score, but also a fun, community-driven initiative that challenges the status quo. It brings a playful yet critical spirit to the table, ensuring that seizure detection research becomes more transparent, reproducible, and ultimately more effective at improving patient care.
And now going back to the original competition, the Seizure Detection Challenge, do we have to use all the tools mentioned in these publications, or can we do our own, just using the main principles mentioned in this chat? Can you also make it relevant to our own tools that we develop, particularly thinking the EEG seizure detection project? I'll provide the link below.
In the context of the Seizure Detection Challenge, you're not strictly required to adopt every single tool mentioned in the published frameworks. What's most important is that you adhere to the core principles of standardization, reproducibility, and rigorous evaluation. The publications such as the ESCOR framework provide a comprehensive blueprint for handling EEG data. They specify uniform data formats like EEG-BIDS with HED score annotations, robust cross-validation strategies, and clinically relevant performance metrics, for example, event-based F1 scores with clearly defined temporal tolerances. That said, you can certainly develop your own tools as long as your approach meets these fundamental criteria. For instance, in our own EEG seizure detection project at RhythmScan, BioniChaos.com/RhythmScan, we've built a custom pipeline that tackles the challenge in a unique way. Our system processes EEG data by converting it into spectrogram images, which are then fed into convolutional neural networks. We employ rigorous data preprocessing, maintain standardized training, validation, test splits, and report detailed performance metrics, including confusion matrices and training logs, to ensure transparency and comparability with other methods. In essence, while the competition guidelines encourage the use of a standardized evaluation framework to facilitate fair comparisons, they also leave room for innovation. If your custom tools implement the main principles such as consistent data formatting, proper cross-validation like leave one out or time series splits for personalized models, and the use of meaningful performance metrics, then you're well within the rules. This flexibility allows you to leverage your own innovations like the interactive spectrogram visualizations and custom CNN architectures in RhythmScan, while still providing results that are comparable and reproducible. It's a win-win. You get to showcase your unique approach, and at the same time, contribute to a more unified, transparent field where everyone's methods can be directly compared.
Now, according to the training data guidelines provided on the challenge webpage, site turn 1 fetch 0, participants are encouraged to work with standardized datasets like CHB, MIT, TUH EEG, and Sienna Scalp EEG. An AI code generator can help you automate the conversion of these diverse datasets into the required EEG-BIDS format with head score compliant annotations. Whether you're using existing tools like the ESL EPFL/epilepsy2BIDS library or crafting your own custom scripts, the AI can provide a robust starting point that you can refine and tailor to your specific needs. The fun part is integrating your AI-generated code into your overall workflow. Picture this. You input a few high-level requirements into your AI code-generating agent, and voila! Out pops code for data preprocessing, model training loops, cross-validation strategies, whether it's leave one out or time series splits for personalized models, and even evaluation metrics reporting. It's like having a high-speed coding sidekick that lets you iterate rapidly, test different hypotheses, and explore innovative ideas without reinventing the wheel every time. That said, while these tools are incredibly powerful, it's essential to critically evaluate and rigorously test any AI-generated code. The competition demands reproducibility and adherence to strict data formats and performance metrics. So make sure to integrate your AI-generated code into a well-documented and standardized pipeline. That way, you not only meet the challenge's criteria, but also maintain full control over the nuances of your seizure detection project. In short, by leveraging an AI code-generating agent, you can supercharge your development process, ensure consistency with the training data standards, site turn 1 fetch 0, and have more time to focus on the innovative aspects of your EEG seizure detection model, all while adding a fun, futuristic twist to the competition.
Yeah, we have some of those datasets already downloaded. We were looking at them already. Actually, yeah, funny thing about this competition, so it's only assuming a 1020, a standard 1020, but a lot of studies that I'm familiar with actually did not use the standard montage. And I have an example of the same dataset converted into spectrogram. I'm doing this training, which actually shows a very high performance, up to 100%, 98% test accuracy. and this is converting essentially this data into spectrograms and doing a seizure detection algorithm. All the code is at the bottom of the page, so using Pillow, library, TensorFlow, so on and so forth. All the code, changing parameters. Yeah, the results here will indicate what model settings were used to actually achieve this result, which is 0 misclassified images in this case. So yeah, so essentially what we will be doing, surely that's okay considering this project is open source, is taking the results of these competitions, hopefully they actually publish the results, and actually deploying them into something useful, going over them. I assume most competitors will be just going for the second dataset there because it has more seizures, but it's important to actually validate the algorithm on a different dataset as well. We could also validate it on synthetic data. Yeah, we had a synthetic EEG signal generator. It's pretty basic. I'm wondering with new models, with ChatGPT O3, whatever mini high, or whenever the actual O3 comes out, actually try and generate code for a better version of this web application. I like doing things in vanilla JavaScript because then it can be deployed anywhere you like this one here. But essentially, if you had the seizure generator as well, so EEG signal generator, but one that has seizures in it, you could be testing one of those algorithms, detection algorithms as well. So hopefully this detection challenge will actually produce some, they will publish the results, the different groups competing, and in theory all this should be open source, well, because the data sets, they do say in the competition that there is like a hidden data that not shown to anyone, that the evaluation is being made on. So that's, yeah, I mean, it's not nice. In theory, something like this will be available after the competition ends, but I don't think this will be the case here. So good luck. Yeah, I don't know what that private data set will be. Interesting if it ever gets into the public domain, or can you like purchase it, or you know what's up with that. In theory, it would have made sense if this dataset was made available after the competition ends, but yeah, follow up on that. I suspect that would not be the case. Some sort of corporate thing. Well, considering, yeah, so it's all like open source without, but then it's sponsored by someone. I don't know who that is. And so they do say that the solutions will be open source. Organizer will write a summary of the outcome. Yeah, everything we do on BioniChaos.com eventually becomes available as open source on our website, BioniChaos.com. So go check it out.